So as you can see from the title, it's about developing a diagnostic tool for identifying skin lesions across all skin tones. There's a bias in AI-powered dermatological diagnostics. So what is the setting? The setting is that we know that skin cancer is potentially life-threatening and that early detection is essential. And so dermatoscopy enhances the diagnostic accuracy. And there are many AI tools already now developed that can assist clinical personnel in defining if a lesion is dangerous or not. Now, the problem is that most existing models are trained on data sets that are dominated by light skin tones. And so this leads to systematic underperformance for patients with darker skin. And of course, then this bias can lead to a delayed or misdiagnosis, which then perpetuates health disparities. So from the point of view of a data scientist, the solution is very simple, right? So just include images of lesions on dark skin in the training data. Why not do that? But there's a problem because let me just shortly introduce you to the International Skin Imaging Collaboration. It's a large database with a very nice, well-curated data set of many skin lesions with hundreds of thousands of those. But if we look exactly like at the metadata, we see that only about a very small percentage of those have the skin tone annotated. For the rest, we just don't know what skin tone the lesion has, and as you can see from here, it's just very difficult to see that I mean, you also don't want to do it manually for 100,000 of images. And then if you look at the 6.5%, we see that if we didn't select only those with dark skin, we have exactly 0 images of cancer on a dark skin. This data just doesn't exist, compared to, for instance, lesions and diagnosis in light skin, which is larger. Of course, one of the reasons for this is that people with dark skin develop so the rate of cancer is much lower. So this is one explanation, but it can't be just the whole explanation. It's just a problem because the data is missing. So this comes now to my project. So my goal is to develop a diagnostic AI tool that's capable of identifying malignant skin lesions across all skin tones. So I have 2 key requirements for my project. The first is to solve the problem of unavailable dark skin images. And for this, I use a tool that is called neural style transfer. In the next slides, I'm going to present to you what it means and how it works. And this allows me to generate artificial yet realistic images. And then I will fine-tune a model on this augmented dataset. And the other key requirement is that I want to ensure privacy of medical data. So if any clinician uses this tool in his clinic, then it shouldn't be necessary to send the image across the internet, but you use it locally. And so therefore, I choose a small model, a fast model, which is the MobileNet V2, which is only 40 megabytes that can very easily deploy it in the browser compared to other models that are much larger. So what is neural style transfer? You probably have already seen pictures like this, where essentially it's an optimization problem where you have a content image and a style image, and then you create an artificially generated image that has the same content as the content image, but essentially in the style of the style image. How does this work? A little bit of detail. So for all of the people here who are interested in that, so essentially it uses a pre-trained VGG 19 network, and then it puts the content image through the network and extracts content features from it, from a very particular layer, but that's not important. And essentially it extracts features that tell you what is in the image. And then you do the same with the content image, which then also extracts features from particular layers. And this one tells you, how does the image look like? And then with an optimization problem, it iteratively then constructs the output image by minimizing some losses. This is what I did with the image. So first of all, I collected several thousand of content images, so like skin lesions on light skin. and also from the same data set, style images. So these style images are this I collected manually, so I looked at it, and it also they were annotated as being from people with dark skin, and they looked like there is no lesion in them. And also, this is why I use, so to say, a style. And then I constructed style transferred images. That's how it's called. So if you see, it looks okay. So the content, like here, this lesion is transferred to here. I mean, the contrast actually here looks better than that. So, but then with using the style that I choose randomly. And with this data set, now I want to train or fine-tune my model. Let me just walk you slowly through the processing pipeline, which was made out of 3 stages. In the first stage, I first chose like a training and validation set that I then used to fine-tune a model. So this is the mobile V2 model, where most of the parts are frozen, small parts are unfrozen, and then they have like a classification head. So there was a trainable and non-trainable part. And this then I fine-tuned. Then in the stage 2, I chose a subset of these images here to have them class balanced, because my data set was very unbalanced. Also chose the style images, so the patches of dark skin that I manually chose. And with those 2 together, I put them through the neural style transfer, which gave me style transfer images, like the ones that I just showed you. And this allowed me in the 3rd stage to then use both of these. Why it's both, it's a complicated detail I don't want to go in, but essentially I then, with these images, I further fine-tuned the same model. So the one that I already trained only on natural images, now I fine-tuned using style transfer images. And then at the end, because I have this tested that I left out, that I didn't use for any fine-tuning, this one I used to do a first test. So first to test how well does a model that uses only natural images able to classify the different lesions in the data set. And then the second test, I test like, does the model suffer from using the style transfer images? Does it perform less good? So the first thing that I'm going to show you is the confusion matrix. We already saw a few today, but just so the confusion matrix shows you how often your model predictions match the true labels, and then breaks this down correct and incorrect guesses for each class. So in the data set, something that I didn't mention, there are 7 lesions, of which melanoma are kind of the most important, because these are the dangerous ones. These are the ones when you detect those, you have to immediately do something. So let's have a look at those. So whenever so there was a melanoma shown on the image, the model was actually pretty good in predicting that. So in 87% of the cases, they predicted melanoma, and only in a few other cases it did not. So this is called the recall. The recall of melanoma was pretty good. On the other hand, if you look at the so-called precision, so this is like how often were images predicted as being melanoma that were not melanoma, the model did not perform very good. So as you see here, very often, like for instance, for this kind of class here, and 37% of the cases that classifies that this is melanoma, although it's not. And this is something that you don't want in a clinical setting, right? You don't want to have like false alarms. So this is something that needs to be worked on. So the F1 score is a nice way of another metric that you can use in order to assess a model that somehow combines precision and recall. And this then I did in order to compare test 1 and test 2. Remember, test 1 is where I only use natural images, and test 2 is where I additionally put the neural transfer images in. And as you can see from the F1 macro, which is kind of the average across all classes, there is a small decrease in performance after putting the neural transfer images into or fine-tuning the model with them. But so weirdly, for some classes, there was even an improvement, but for others, like a very strong decrease in performance. And for melanoma, was about like the same as the average, so a small decrease. Now, another metric, and this is one that's very important in the clinical context, is the top 3 accuracy. So it reflects clinical triage scenarios where let's say a clinician wants to know like how sure is it that there's melanoma in the data or not. So let's have, for instance, let's say we have these 3 scenarios here. So let's say there's an image, it goes through the model, and the output is the one at the top. So in that case, the clinician will know for very sure there is no melanoma in it. I don't need to do anything about it. Two other cases are different. In the top one, it's very clear that it is melanoma. And in this one, the classifier is just not sure. There's a 50-50 chance of it being melanoma or maybe something that is benign. But this having this helps the clinician to say, okay, I have to deal first with this case because this is like very clear, and then only then I will deal with this case. So this is what is called triage. I think that's how it's pronounced. So if we look at the top 3 accuracy of both models, so the one trained only on natural images and the one trained additional with the neural transfer images, we see that it's pretty good actually. So top 3 accuracy of 93% of the second model means that in more than 9 out of 10 cases, the correct answer was in one of the top 3 categories. A deployed model is very, very simple, nothing fancy at all. So you can select the image to put an image here, or you can do a drag and drop. I also, just for demonstration purposes, I already put like 4 examples in here. So this is, for instance, so this is the melanoma, and the classifier correctly predicted that being melanoma. But wait, so this is actually the original. So this is the natural image. With this one, I did then the neural transfer. And here you see that the classifier loses a little bit of precision, right? Here, this is a nevus, which is like the stuff that we all have everywhere, which is very harmless. In the natural image, the classifier predicts correctly as it just being the nevus. But then, for instance, if you look at the style transferred one, it loses something happened during the neural transfer. It lost a lot of features that were essential for the classification, and now it's only in the 3rd place, so it's not really working. Maybe some of you have already thought, well, but the actual ultimate test is missing, right? So I mean, what I wanted to do is to do a tool that can correctly classify skin lesions that are on dark skin images, but so I would need those data, but as we already saw in the beginning of the presentation, those data just don't exist. So I can't do this ultimate test that I would need to do in order to really assess this tool. So one way would be to collaborate with dermatology clinics in order to collect diverse data. This is just the only way to do that. Then there's the low precision of melanoma that's concerning. If you remember, a lot of false alarms that you don't want to have. So this is something that where also the baseline model, even before augmenting it with style transfer data, needs to be improved. And then in the end, we saw that there is the style transfer approach the quality is not always consistent. In some cases, the features are correctly transferred. In other cases, don't, so that the tool or the model suffers from that. So that needs parameter tweaking further. And with that, I would first of all like to thank my wife, who had like a very important part in motivating this project. And I would like to thank you for your attention.